Good day everybody. Before we could head on to see other standard substitutions and how to handle them, let us first observe these following integrals. These are all interesting integrals and we will complete these integrals and then we will move on to handling integrals by means of standard substitutions. So I mentioned that let's see how we can handle this question. We are expected to integrate integral dx over 4th root of x negative 1 raised to the power of 3 times x positive 2 raised to the power of 5. So I would like to rewrite this as integral dx over x negative 1 raised to the power of 3 times x positive 2 raised to the power of 5. This entire quantity is raised to the power of 1 over 4. Now this can be further rewritten as integral dx over x negative 1, apply this 1 over 4 to the quantities inside, and that is going to give me x negative 1 raised to the power of 3 over 4 times x positive 2 raised to the power of 5 over 4. Now what I wish to do is I would like to take x negative 1 out. Now if I were to take x negative 1 out, what would be the outcome? That's an interesting question. The idea is actually to bring x negative 1 inside this exponent power of 5 over 4. So I would like to write this quantity x positive 2 raised to the power of 5 over 4 as x positive 2 divided by x negative 1, and the whole quantity I wanted to raise it to the power of 5 over 4. How is that possible? That is possible only if I can multiply and divide by x negative 1 raised to the power of 5 over 4. Right, not by 3 over 4 but by 5 over 4. So I am actually multiplying by 1 over x negative 1 raised to the power of 5 over 4. So I can now write this quantity as x positive 2 divided by x negative 1 raised to the power of 5 over 4. But that would mean I am additionally bringing in x negative 1 raised to the power of 5 over 4. So I need to counter this. So that is countered by multiplying the numerator by x negative 1 raised to the power of 5 over 4. So clearly x negative 1 raised to the power of 5 over 4 and x negative 1 raised to the power of 5 over 4, they get cancelled. So I am actually multiplying by 1, which will not have any impact. So that is the idea. So now this is rewritten as integral dx divided by, so I'm going to start off with this term x positive 2 divided by x negative 1. This is raised to the power of 5 over 4 times, I'm clubbing these two together, x negative 1 raised to the power of 3 over 4 times x negative 1 raised to the power of 5 over 4. Now a raised to the power of m times a raised to the power of n is a raised to the power of n positive n. So by this I can rewrite this as integral dx over, this stays as it is, x positive 2 divided by x negative 1 raised to the power of 5 over 4, and this is going to be x negative 1 raised to the power of 3 over 4 positive 5 over 4. So let me move on here. So this is equal to integral dx divided by x positive 2 divided by x negative 1. This is raised to the power of 5 over 4, and this is going to be 8 over 4. That's going to be x negative 1 raised to the power of 2. So this is what you've got. Now I did all of this thing to allow me this substitution. Let x positive 2 divided by x negative 1 be equal to sum u. So you differentiate this by u over v. That means x negative 1 times differential of x positive 2 is going to be 1 negative x positive 2 times differential of x negative 1 is going to be 1 divided by x negative 1 raised to the power of 2. This is equal to du. So this is going to give me x negative 1 negative x negative 2 divided by x negative 1 raised to the power of 2 Of course, you have this dx there, differential operator. You can place that. Now, when positive x, negative x gets cancelled, giving me negative 3 over x negative 1 raised to the power of 2 times dx is equal to du. So, you got dx over x negative 1 raised to the power of 2 is equal to du over 3 with a negative sign. So therefore, if you were to look into the question, integral dx over x positive 2 divided by x negative 1 raised to the power of 5 over 4 times x negative 1 raised to the power of 2, you can rewrite this as integral in place of this quantity. This is going to be my u, so you can substitute that, and in place of this entire quantity dx over x negative 1 raised to the power of 2, this is going to be du divided by 3. I can place the 3 there and there is a negative sign, so this is what I've got, and this is raised to the power of 5 over 4, so you place that 5 over 4 there. So this can be rewritten as negative 1 over 3 integral u raised to the power of negative 5 over 4 times du. You integrate this, you get u raised to the power of negative 5 over 4 positive 1 divided by negative 5 over 4 positive 1. This is negative 1 over 3, and you get u raised to the power of negative 5 positive 4 divided by 4 divided by negative 5 positive 4 divided by 4. That's simplification. So that is equal to negative 1 over 3 u raised to the power of negative 5 added with 4 would give me negative 1 divided by 4 divided by negative 1 over 4. This is equal to negative will become positive, so you get 4 over 3 u raised to the power of negative 1 over 4. You push this down, you get 4 over 3 times 1 over u raised to the power of 1 over 4, which is equal to 4 over 3, 1 over, my u is x positive 2 divided by x negative 1, that is raised to the power of 1 over 4. Now you can flip this, this is equal to 4 over 3, you flip it, you get x negative 1 raised to the power of 1 over 4 divided by x positive 2 raised to the power of 1 over 4. You can rewrite this as 4 over 3 x negative 1 divided by x positive 2. This is raised to the power of 1 over 4, positive arbitrary constant c. Now this is a lovely question. Integral x squared negative 1 divided by x to the power of 3 times square root of 2 times x to the power of 4 negative 2x squared positive 1 times dx. Now foremost, what I wish to do is I would like to take from the denominator x to the power of 4, and then I rewrite this as 2 negative 2 over x squared positive 1 over x to the power of 4. Of course, this entire thing is inside the square root, so let me place the square root, and you have x to the power of 3 there with the integral sign times dx. Now let me push this x to the power of 4 out of the square root, so that would give me x to the power of 4. When it comes out, it will become x squared, and you got the square root. You have 2 negative 2 over x squared positive 1 over x to the power of 4, and you have x to the power of 3 there. Okay, so now what I wish to do is I would like to take this x squared out. Now if I were to do that, this is going to be x squared of 1 negative 1 over x squared and this is divided by x to the power of 3 times x squared square root of 2 negative 2 over x squared positive with the integral sign. Now clearly I can cancel this x squared and x squared, so that would give me equal to x to the power of negative 3 times 1 negative 1 over x squared times dx divided by square root of 2 negative 2 over x squared positive 1 over x to the power of 4 with the integral sign. So let me change the color. Now just distribute x to the power of negative 3. That would give me x to the power of negative 3 negative x to the power of negative 3 divided by x squared times dx divided by the denominator. Now bring x to the power of negative 3 to the denominator. So this is equal to 1 over x to the power of 3 negative 1 over x to the power of 5 divided by square root of, I'm going to place the quantity 2 negative 2 over x squared positive 1 over x to the power of 4 times dx. Now we need to make a substitution. Now let me take the substitution. Let 2 negative 2 over x to the power of 2 positive 1 over x to the power of 4 be equal to some t. Now if I were to differentiate this is going to be 0. Now this is actually, let me have one more step. This is going to be 2 negative 2 times x to the power of negative 2 positive x to the power of negative 4 is equal to t. Now if you were to differentiate this, you get 0 negative, this is 2 times negative 2 times x to the power of negative 2 negative 1 positive of negative 4 times x to the power of negative 4 negative 1 times dx is equal to dt. Now this can be rewritten as negative 2 is 4 times x to the power of negative 3 and negative 4 x to the power of negative 5 times dx is equal to dt. I can rewrite this by taking 4 out. So let me take 4 out. So this is going to give me 4 is taken out. 1 over x to the power of 3 negative 1 over x to the power of 5 times dx is equal to dt. Now what do you have in the numerator? 1 over x to the power of 3 negative 1 over x to the power of 5 times dx. So that's exactly what you got. So this can be rewritten as 1 over x to the power of 3 negative 1 over x to the power of 5 times dx is equal to dt over 4. So if I were to take this as a, then I can rewrite a as follows. So therefore a is rewritten as integral. In place of the numerator, I'm going to substitute dt over 4. In place of the denominator, so we have taken this to be as t, right? So this is t raised to the power of 1 over 2. Now I can take it to the numerator. So it's 1 over 4 integral t raised to the power of negative 1 over 2 times dt. If you were to integrate this, this is going to give me 1 over 4 times t raised to the power of negative 1 over 2 positive 1 divided by negative 1 over 2 positive 1, which is equal to 1 over 4. Now this will give you a positive 1 over 2 and a positive 1 over 2. You flip this, you get 2 over 4 times t raised to the power of 1 over 2, which is equal to 1 over 2 times t. But what is my t? My t is this quantity, 2 negative 2 over
So substitute that 2 negative 2 over x squared positive 1 over x to the power of 4 raised to the power of 1 over 2. Final answer, this is equal to 1 over 2 times square root of, I'm going to use the square root sign now, square root of 2 negative 2 over x squared positive 1 over x to the power of 4. Since it's indefinite, you got to add this arbitrary constancy. So this is the final solution for this particular question. Majority of the people who are doing this question will for sure make a mistake. Now I will also show you where they will make a mistake. So having mentioned that particular information, let me use technique of substitution. So this is the question given, integral 2x negative 1 times cos of root of 2x negative 1 raised to the power of 2 positive 5 divided by square root of 2x negative 1 raised to the power of 2 positive 5 times dx. Now I am going to make the substitution, let 2x negative 1 raised to the power of 2 positive 5 be equal to t squared. I differentiate, I get 2 times of 2x negative 1 raised to the power of 2 negative 1 times, this is the place where people will make a mistake. You need to differentiate 2x also. So differential of 2x is going to be 2 multiplied with the differential operator dx, because differentiation of constant phi is going to give me 0. People will miss this 2, and that is the important point that you need to pay attention to. So this is equal to 2 times followed by t raised to the power of 2 minus 1, that's going to be 1 there, times dt. So you can cancel the 2 here, So this is rewritten as 2 times of 2x negative 1 times dx is equal to t dt. Now I need only dx, so this is dx is equal to t dt divided by 2 times of 2x negative 1. So we need to extract the value for 2x. So I'm going to do that over here. So before I could head out, let me just box this off and perform the operation over here. Okay, so 2x negative 1 raised to the power of 2 is equal to t squared negative 5. Because I'm moving the 5, I am interested in 2x negative 1. So move the 2 to the other side, so you will be getting 2x negative 1 is equal to square root of t squared negative 5, and if I were to rewrite dx, it can now be rewritten as t times dt divided by 2 times 2x negative 1 is going to be square root of t squared negative 5. Now go back to the problem. Let me place a divider. So this question is rewritten as integral 2x negative 1, that's going to be square root of t squared negative 5 times cos of square root of 2x negative 1 raised to the power of 2 positive 5, that's going to be t squared divided by root of 2x negative 1 raised to the power of 2 positive 5, that's going to be root of t squared, and dx, this is another place people will make a mistake. So make sure that dx is t times dt over 2 times root of t squared negative 5. So root of t squared negative 5, t squared negative 5 cancels, t and root of t squared gets cancelled. So this is equal to 1 over 2 is there, take that 1 over 2 out. Cos of root of t squared, that's going to be cos t times dt. You integrate this, you get 1 over 2 times sin t, but I need only t. T is root of this value, right? So this is equal to 1 over 2 times sine of square root of, it's 2x negative 1 raised to the power of 2, 2x negative 1 raised to the power of 2, positive 5. Let me check it out. 2x negative 1 raised to the power of 2, positive 5. Positive, you need to place the arbitrary constant c. So this is the final answer to the question. Okay, so I hope you can see that.
Welcome students. In this class we will learn about standard substitutions. Now suppose you have a form like this, integral dx over a squared negative x squared. Now it can either be like this or it may also be like this, integral dx over square root of a squared negative x squared. Now if you have, say, let me just start off with this. Suppose they are asking us to solve a question, say solve or integrate. I think the question can be asked in any manner. Say dx divided by 16 negative x squared. We are expected to integrate. Now you can integrate this using partial fractions or by standard substitution. If you approach by standard substitution, you will be able to solve this in a much faster and easier manner. So what is the standard substitution? Now foremost, rewrite this as integral dx over this 16 has to be written in form of a square. So I'm going to write it as 4 squared negative x squared. Then you make the following substitution. Let this x be equal to, you take one constant raised to the power of 1. So when I say one constant, I'm talking about this constant which is in this particular question. So that constant is 4. Then you will have to make a substitution as 4 times, say, sine theta, or you can make a substitution as 4 times cos theta. Apart from these two substitutions, you cannot utilize any other thing. Either this goes or this goes. If you choose to approach this question in some other manner, you will be just circling around. You won't be able to solve this. So this is the all important note. Either you can take x is equal to 4 times sine theta or x is equal to 4 times cos theta. I would be taking x is equal to 4 times sine theta. Why? Because when I differentiate, I would just get a positive value. So it's going to be 4 times cos theta d theta. Because if I were to use x is equal to 4 times cos theta, when I differentiate, I would get a negative quantity. And dealing with negative quantity is can be a little bit complicated. Why? Because you might slip that negative sign out, and even though you give the result, you might think it's correct, but it wouldn't be, because if you were to drop the negative sign in the final result, still the question is not solved. So having given you that information, let me move on. So in place of dx, I'm going to substitute 4 times cos theta times d theta divided by 4 squared negative. In place of x, it's going to be 4 sine theta raised to the power of 2. So that's going to be 4 squared sine squared theta. I'm going to rewrite this as integral. 4 is actually a constant which is featuring everywhere. Take that out, place cos theta d theta. Now take a 4 squared out, and that would give me 1 negative sine squared theta. Now there is a trigonometric identity which says that sine squared theta added with cos squared theta is equal to 1. So from here I can rewrite cos squared theta is equal to 1 negative sine squared theta. So we know that. So if I were to utilize, in place of 1 negative sine squared theta, cos squared theta, this is going to be integral. I can cancel 4 out, so it's going to be 1 over 4 times integral cos theta d theta divided by cos squared theta. I can cancel cos out, so it's going to be 1 over 4 integral of d theta divided by cos theta. Now this cos theta is nothing but 1 over 4 times integral 1 over cos theta is written like this, 1 over cos theta times d theta, right? Now what is this 1 over cos theta? 1 over cos theta is nothing but secant theta d theta. Now you have to get the value for secant theta, integral of secant theta. Now I have already given you a formula for integral of secant theta, and I will be utilizing that formula over here. So utilizing this formula, I would be getting for integral of secant theta ln modulus of secant theta positive tan theta. Now I already have this 1 over 4, so just place that 1 over 4. Now this is not the final answer. Why? Because we have taken sine theta with the product multiple of 4 being equal to x. So from here, what I wish to do is I would like to extract the value of sine theta. So sine theta is equal to x divided by 4. So you go to the Pythagoras triangle. So when I say Pythagoras triangle, I am talking about the right triangle. If I were to take this as A, B, C, this to be as theta, this is 90 degree. So this is going to be my opposite side, this is my adjacent side, this is my hypotenuse side. So the trigonometric identity for sine theta in terms of ratios is sine theta is equal to opposite side divided by hypotenuse. So my opposite side is x over 4. So this is going to be my x and this is going to be my 4. So I would have to get the adjacent side. So for that, just to utilize, I would be using this part, utilize the right triangle identity, the Pythagoras one. So it's AB squared plus BC squared is equal to AC squared. So I need AB squared. So AB squared is equal to AC squared negative BC squared. So AC squared is 4 squared and my BC squared is x squared. So we need only AB. So AB is equal to square root of 4 squared negative x squared. So that goes down over here. 4 squared negative x squared. Now we have to get the value of secant theta and tan theta. Now secant theta is 1 over cos theta. Now what is the ratio for cos theta? Cos theta is, let me place here, cos theta is adjacent side divided by hypotenuse. And now what is adjacent side? Square root of 4 squared negative x squared. Hypotenuse is 4. Now we place the value here, square root of 4 squared negative x squared divided by 4. You flip this, what do you get when you flip it? You get 4 over square root of 4 squared negative x squared. So this is for secant theta. So go over here, place that value, 1 over 4 times ln of secant theta is 4 over square root of 4 squared negative x squared positive. I need to get tan theta. Now what is tan theta? I will just try to squeeze it over here. Tan theta is sine theta divided by cos theta. Now what is sine theta? Sine theta is x divided by 4. And what is cos theta? Cos theta is square root of 4 squared negative x squared divided by 4. So you flip it. When you flip it, you get x over 4 times 4 over root of 4 squared negative x squared. 4 gets cancelled, giving me x over square root of 4 squared negative x squared. So you substitute that, x over square root of 4 squared negative x squared. This is modulus sign. Okay, you got to place the modulus sign. So this is 1 over 4 times ln of, the denominator is square root of 4 squared negative x squared, and in the numerator you got a 4 and a x. So you place this in modulus. Okay, now you can actually rewrite this. You can actually rewrite this as 1 over 4 times ln. Now can I write this as root of 4 positive x times square root of 4 positive x? Can I do that? Of course, root of 4 positive x times root of 4 positive x gives me 4 positive x because of the properties of square root. Now, can I rewrite this as root of 4 negative x multiplied with 4 positive x? Can I do that? Of course I can do that, because a negative b multiplied with a positive b will be giving me a squared negative b squared, and I am placing it within the square root, so this is going to be root of a squared negative b squared. Okay, so that is fair enough. Now come back over here. So this is equal to 1 over 4 times ln. Now can I rewrite this as root of 4 positive x multiplied with root of 4 positive x divided by square root of 4 negative x times square root of 4 positive x? Can I do that? Of course I can do that, because root of a into b is root of a times root of b. Now can I cancel this with this? Yes, I can. Now can I rewrite this as 1 over 4 times ln modulus root of 4 positive x divided by root of 4 negative x followed by an arbitrary constant? Yes, I can do that. So that is the solution for this question. Now I can actually utilize the formula. Now there is a formula for this one: integral dx over a squared negative x squared is equal to 1 over 2 times of a times ln modulus of a positive x divided by a negative x positive c. So that would mean, if you want to split this in this fashion, is to rewrite this final answer 1 over 4 times ln modulus of root of 4 positive x divided by 4 negative x positive arbitrary constant c as, I gave you this formula: integral dx over a squared negative x squared is nothing but 1 over 2 times a ln modulus of a positive x divided by a negative x. I want to rewrite this in this fashion. So how do I do that? Now this is equal to 1 over 4 times ln. Now you have a square root, so can I write it like this: 4 positive x divided by 4 negative x? Yes, I can write it. So now moving forward, can I write this like this: 4 positive x divided by 4 negative x raised to the power of 1 over 2 modulus? Can I write it like this? Of course I can write it. Now I know that ln a over a raised to the power of b is equal to b times ln a. Now can I rewrite this as 1 over 2, I can bring this 1 over 2 times 1 over 4 times ln modulus of 4 positive x divided by 4 negative x positive arbitrary constant c. Can I do that? Yes, I can do that. So can I further complete the solution as 1 over 2 times of 4 ln modulus 4 positive x divided by 4 negative x positive c, which is similar to 1 over 2 times a ln modulus of a positive x divided by a negative x positive c, where the value of a is equal to 4. Why? Because of the question, integral dx over 16 negative x squared is nothing but integral dx over 4 squared negative x squared, which is similar to integral dx over a squared negative x squared. Now I did all of this to show you how exactly we can literally use this formula to directly write the output. When I say output, I mean the solution. We can directly write the solution. Now there is also another side of this problem. Now if they ask you to solve this or to integrate this completely without using formula, then you need to adopt this approach. Now there is also the partial fraction type approach, but since I'm talking about standard substitution, I would like to restrict my solution to substitution technique. Okay, now having given you this technique of substitution, I would like to have a note here. Now if you remember, I mentioned to you that we have already seen integral of secant theta d theta to be equal to ln modulus of secant theta positive tan theta. Now this formula can also be rewritten as 1 over 2 times ln of 1 positive sine theta divided by 1 negative sine theta. So sometimes you might see integral secant theta d theta to be equal to ln of modulus of secant theta positive tan theta, or else you can also see it to be as 1 over 2 times ln of 1 positive sine theta divided by 1 minus sine theta, or further you might also see it to be as ln modulus of tan of theta over 2 positive pi over 4. So this is also possible. In each of these cases you need to place the arbitrary constancy. Now the question is, you might be wondering, what is this? How come from here you are getting this, and how come from here you are getting this? So I am going to show that result to you. Now what we are going to utilize is what is called as the tangent of angle substitution. So this substitution is important. Okay, so what is the substitution? We take t to be as tan theta over 2 and subsequently sine theta to be as 2 theta divided by 1 positive t squared, and cos theta is taken to be as 1 negative t squared divided by 1 positive t squared. Okay, so that is the substitution that we will be utilizing for tan, sine and cos. So when I say tan, it's tan theta over 2. Okay, and the rest of the things for sine and cos, they are just sine theta and cos theta. Now this is very important off angle substitution that you will have to know if you want to become invincible in calculus. Then these half angle substitution should be written in your memory. Okay, now since I mentioned to you this, the question is, how am I going to show this is equal to this? So for that, let me just consider this particular quantities. Say, let me just go on to show you that square root of 1 positive sine theta divided by 1 negative sine theta. Now if I were to apply ln, this is what I get, ln of square root of 1 positive sine theta divided by 1 negative sine theta. Now this can be rewritten as ln of 1 positive sine theta divided by 1 negative sine theta raised to the power of 1 over 2, which is nothing but 1 over 2 times ln of 1 positive sine theta divided by 1 negative sine theta, right? So what I'm going to show you is, I'm going to show that square root, because this is the quantity that is actually varying. In place of secant theta positive tan theta, I have got square root of 1 positive sine theta divided by 1 negative sine theta. So my game or my idea is to show that root of 1 positive sine theta divided by 1 negative sine theta is same as secant theta positive tan theta, which in turn is same as tan of theta over 2 positive pi over 4. So if I can show all these things are equivalent, that means I can very well substitute in place of this, I can substitute this, and in place of this I can substitute this. So that's the main idea. So for that, what I'm going to do is, I need to first consider this quantity, square root of 1 positive sine theta divided by 1 negative sine theta. As I just mentioned to you, I have half angle, tan half angle substitution as 2t divided by 1 positive t squared. So substitute that, 2t divided by 1 positive t squared divided by, drag the square root, 1 negative 2t divided by 1 positive t squared. So this is equal to square root of 1 positive t squared positive 2t divided by 1 positive t squared over 1 positive t squared negative 2t divided by 1 positive t squared. So these two terms gets cancelled. Now this is equal to root of, what is this? This is 1 positive t raised to the power of 2, and what is this? This is 1 negative t raised to the power of 2. Now the square root sign, the radical sign and the square, they get cancelled, so giving me 1 positive t divided by 1 negative t. Now it's better to put them in the modulus sign. So this is what I get for this. Now let me go and see what I exactly get for secant theta positive tan theta. So I will just put them in the modulus sign. So now the all important question comes, how are we going to handle the secant theta positive tan theta? So let me just go to the next page and handle that. So consider, so this is what I've got, square root of 1 positive sine theta divided by 1 negative sine theta leads me to this quantity. Now if I can prove, if we can show that secant theta positive tan theta also equals to 1 positive t divided by 1 negative t, this means square root of 1 positive sine theta divided by 1 negative sine theta is equal to secant theta positive tan theta. You place the modulus if you want on both sides, or you can just go ahead with the proof. So I'll just place the modulus to avoid any issues. So now the question is, let me just actually find out what is this. So I'm going to consider secant theta positive tan theta. Now secant theta is 1 over cos theta, and tan theta I'm going to write it as, sin theta divided by cos theta. Now since cos theta is 1 negative t squared divided by 1 positive t squared by tan half angle substitution, and sin theta is 2t divided by 1 positive t squared, so this is going to be equal to 1 over 1 negative t squared divided by 1 positive t squared positive 2t divided by 1 positive t squared divided by 1 negative t squared divided by 1 positive t squared. You flip it, you get 1 positive t squared divided by 1 negative t squared positive 2t divided by 1 positive t squared times 1 positive t squared divided by 1 negative t squared. 1 positive t squared, 1 positive t squared gets cancelled. So this is equal to modulus of what we got here, 1 positive t squared divided by 1 negative t squared positive 2t divided by 1 negative t squared. The denominators are same, so 1 negative t squared, 1 negative t squared, and this is going to be 1 positive t squared positive 2t. This can be rewritten as 1 positive t raised to the power of 2 divided by 1 negative t squared. Now this can be further rewritten as 1 positive t times 1 positive t, right, with the modulus, divided by 1 negative t squared is written as 1 negative t times 1 positive t. 1 positive t, 1 positive t gets cancelled, giving me modulus of 1 positive t divided by 1 negative t. Now what is this? What is this? This is exactly what we've got. You see that? This is what we have got, 1 positive t divided by 1 negative t, which is equal to the value root of 1 positive sine t divided by 1 negative sine t, right? This is exactly what we wanted to show. So this on the left hand side is what, modulus of secant theta positive tan theta. So both of them are one and the same. So now the question comes is it equal to this? So I need to go for this now. So consider tan of theta over 2 positive pi over 4. Now we have a formula. What is the formula? We know that tan of a positive b is tan a positive tan b divided by 1 negative tan a tan b. So applying this formula over here, this is going to be tan theta over 2 positive tan pi over 4 divided by 1 negative tan theta over 2 times tan pi over 4. Tan theta over 2 we know by half angle, tan half angle substitution is t. This is 1, this is 1 negative tan theta over 2 is t, this is 1, so I can rewrite this as 1 positive t divided by 1 negative t. If you are taking the modulus, this will result in the modulus. So this means this is equal to this and this is equal to this, and hence I can substitute in place of this I can substitute this, in place of this I can substitute this. So all these three quantities are equivalent, and we have done that. We have established it by tan half angle substitution. So this is a very important concept, and we have done it well, and we'll move on to the next. Now continuing on our study on standard substitution. Now suppose you have a quantity like this, integral of dx over a squared positive x squared. Now if the denominator has got a squared positive x squared or square root of a squared positive x squared, then you can use this substitution, x is equal to a tan theta or x is equal to a cot theta. Apart from this, don't adopt any other substitution. Of course you can approach or utilize partial fractions, but then again, as I mentioned to you, it depends on the complexity of the question. So we are dealing with substitution technique, so I'm introducing you these two substitutions. So either you can utilize this or you can utilize this. Now imagine I have a question, say integral dx over 25 positive x squared. I need to integrate this. Now I can utilize the formula. There is also a formula which we will show or deduce. Now given this question, foremost what I wish to do is I would like to rewrite this as integral dx over 5 squared positive x squared. Then I will make the following substitution. Let x be equal to 5 times tan theta. Now if I were to differentiate x, I get dx. Differential of tan theta is secant squared theta times d theta. So in place of dx, you substitute 5 times secant squared theta d theta. In place of x, you substitute 5 tan theta. So that's going to be 5 tan squared theta. You can take 5 out, you get secant squared theta d theta divided by, you can take 5 squared out, you get 1 positive tan squared theta. Now we know a formula, trigonometric identity, as secant squared theta negative tan squared theta is equal to 1, and secant squared theta is equal to 1 positive tan squared theta. So by that substitution, of course I can cancel a 5 here. I will get 1 over 5 times integral secant squared theta times d theta divided by secant squared theta. Secant squared theta gets cancelled, giving me 1 over 5 integral d theta. Integral of d theta is going to give me theta. Now since I've taken the substitution x is equal to 5 times tan theta, I can rewrite this as tan theta is equal to x over 5, and then I can rewrite theta to be as tan inverse of x over 5. So this is the value for theta. So substitute it here. So it's going to be 1 over 5 times tan inverse of x over 5 plus arbitrary constancy. So that means we have got a trigonometric formula, dx over a squared positive x squared. Now this is very much similar to integral dx over 25 positive x squared. So what did we do? We rewrote it as integral dx over 5 squared positive x squared. And what is the result? We got 1 over 5 times tan inverse of x over 5 positive arbitrary constancy. So in a similar manner, if I were to superinflate this result over here, this is going to be 1 over a tan inverse of x over a positive arbitrary constancy. So this is a very important result, and we can utilize this result in many questions. So I mentioned you that. Let me move on to the next substitution. Now we have been dealing with a squared positive x squared, our terms without any square roots. Now what if you were to get a square root over here? Say, let me do that. Instead of integral dx over 25 positive x squared, what happens if we have got something like this, integral dx over square root of 36 negative x squared? Now this is actually rewritten as integral dx over 6 squared negative x squared. So as I mentioned to you in the start of this question, whenever you have form like 6 squared negative x squared, I take the substitution as x is equal to 6 times sine theta. Of course you can take x is equal to 6 times cos theta, but I've told you the reason why I'm taking x is equal to 6 times sine theta. So if I were to differentiate, I get 6 times cos theta times d theta. So this is equal to integral, in place of dx it's going to be 6 times cos theta d theta divided by root of 6 squared negative. In place of x I would substitute 6 sine theta. It's going to be 6 squared times sine squared theta So 6 can be taken out. So this is going to be cos theta d theta divided by 6 times root of 1 negative sine square theta. Now we know that 1 negative sine square theta is equal to cos square theta. So this is equal to 6 and 6 can be cancelled. So we got integral cos theta d theta divided by root of cos square theta. You apply the square root, you get cos theta times d theta. Cos theta can be cancelled, giving you integral d theta. Integration of d theta is going to be theta. Now coming back over here, since x is taken to be as 6 times sine theta, x over 6 is equal to sine theta. We need only theta, so therefore theta is equal to sine inverse of x over 6. So substitute it sine inverse of x over 6, positive arbitrary constant c. So therefore you have a beautiful result. So what is the result? If you got integral dx over root of a squared negative x squared, now this is equal to sine inverse of x over a, positive arbitrary constant c. So this is a beautiful outcome of the substitution technique. Now what if I have got, say, integral dx over root of, say, 25 positive x squared? How would you handle this question? So a question like this, as I mentioned to you, whenever you get positive x squared, take substitution as x is equal to 5 times tan theta, because this can be rewritten as integral dx over square root of 5 squared positive x squared. So if I were to substitute this, I would get square root of 5 squared positive 5 squared tan squared theta. Of course I need to get a dx here. Dx will be 5 times secant square theta d theta. So 5 times secant square theta d theta. So this is equal to 5 can be taken out. So you got a secant square theta d theta. So I take 5 out, I get 1 positive tan square theta. Now 1 positive tan square theta, we know that 1 positive tan square theta is secant square theta. So substitute that, 5 gets cancelled. You get integral secant square theta d theta divided by root of secant square theta. So root of secant square theta will give you secant theta. So secant theta and secant theta gets cancelled, giving you integral of secant theta d theta. Now I've shown you how to integrate this. This is nothing but ln modulus of secant theta positive tan theta. Now we can actually go further, right? Because this can be replaced. Based on the substitution, I can actually replace this with the values that we have here. Now since I've taken, now we need to do that. Since I've taken x is equal to 5 times tan theta, so x over 5 is equal to tan theta, right? So you make up the right triangle property. So this is adjacent side, this is opposite side, this is hypotenuse side. So I'll take it as a, b, c. Now tan theta is opposite side divided by adjacent side. So that means you got an x here, you have a 5 here. So hypotenuse side is going to be, so that has to be placed there. So therefore secant theta, is going to be square root of x squared positive 5 squared divided by 5. So go up over here and substitute this. So this is going to be ln modulus square root of x squared positive 5 squared divided by 5 positive tan theta is x over 5 modulus. This is ln of, the denominator is 5, so it's going to be root of x squared positive 5 squared positive x. So this is what we have got. Now the point is that we will have to get rid of this 5, right? So we can also do that. Now this is the all important part here. Now this is actually ln of a over b. Let me write that over here. Ln of a over b, which is nothing but ln a negative ln b. Now I would be utilizing that over here. So I would get ln modulus of square root of x squared positive 5 squared positive x negative ln of 5 positive arbitrary constant c. But when we write the final result, we will rewrite this quantity as ln modulus square root of x squared positive 5 positive x. We will not mention this negative 5, negative ln of 5. What we do instead, we actually club it with this arbitrary constant c, right? So in other words, this constant gets absorbed by this constant c, and we write the final result as positive c. So that is the very important concept that you will have to know, because most times when you integrate, this is the value that you will get, but the final answer has to be specified in this fashion, because of the fact that we are getting a ln c, ln 5, and that ln 5 is being absorbed by this arbitrary constant, and subsequently this is the result. Of course, when we are dealing with integration of hyperbolic function, I will touch this question again in a different fashion.